For test 2, question 1, we know the 4 charges. Q1 is positive, Q2 is positive, Q3 and 4 are negative. The magnitude of those charges is twice the magnitude of these charges. It tells us that there's going to be some symmetry here in these problems. They're arranged on a square diamond, that's just a square rotated by 45 degrees, and the side length is 10 millimeters. Draw the electric fields due to each of the 4 charges at the center. Label each field clearly and draw them approximately to scale. Since these charges are twice as big as these charges, the electric field due to these charges is going to be twice as long as the electric field due to these charges. So let's get started. The electric field at point P due to charge 1 points away from charge 1 because it's a positive charge. Electric field E1 points towards Q3 because Q3 is negative. Okay, it's about twice as long here. At point P due to charge 2, it points away from point P. 2 and 1 have the same charge, so they're approximately the same length. We point towards charge 4, and that's twice as long as E2 because the charge is twice as big, and it's the same length as E3. So there's part A done. Find the net electric field vector at point P. For this one, we're going to make heavy use of the symmetry in this problem, knowing that these 2 charges are equal, and these 2 are twice as big, and everything is equidistant from their charges. To find the electric field, we know it's the net field, and this is a vector sum, due to each of the individual 4 charges. Okay, so if we want to find the vector sum, we need to find the vector components. So the magnitude of electric field E1 is K times the magnitude of charge 1 divided by the distance R1 squared. K is 8.99 times 10 to the 9 newtons meters squared over coulombs squared. The magnitude of charge 1 is 2.5 microcoulombs. 2.50 times 10 to the minus 6 coulombs. Want to divide by R1 squared. Let's make sure we know what R1 is. Let's label R1 in our picture. R1 is the distance from charge 1 to our point. R2, let's just do all of them while we're here, is between charge 2 and our point. R3 is from here to here. My diagram's a bit full, I'll write that over on the side. And R4 is from here to here. I'll write that just down a little bit below. We're all from a corner to the center, so those all have the same magnitude. R1, 2, 3, and 4 are all the same. We could call that R if we wanted. We see that this is a right angle triangle, so R1 squared plus R2 squared equals L squared. R squared equals L squared. R is equal to L divided by root 2. So 10 millimeters divided by root 2, 7.071 millimeters. Okay, there's our R value. So we're dividing by 7.071, got to put that in meters, times 10 to the minus 3 squared. Gives us a magnitude of electric field equal to 4.495 times 10 to the 8 newtons per coulomb. There's the magnitude of our first electric field. Remember, we're doing a vector sum, so we need components. E1 doesn't point left or right, so E1x equals 0. The y component points straight down, so it's negative, and it's the whole thing, so it's minus 4.495 times 10 to the 8 newtons per coulomb. Okay, let's start getting into our symmetry now. The magnitude of E2 is the same as the magnitude of E1 because we have the same charge at the same distance. 4.495 times 10 to the 8 newtons per coulomb. The x component, E2x, is positive because it points to the right. Oh, sorry, negative because it points to the left. Let's put my coordinate system up here. So minus 4.495 times 10 to the 8 newtons per coulomb. The y component is 0 because it doesn't point up or down at all. Okay, so now for the magnitude of my electric field vector, E3. Charge Q3 is twice as big as charge Q1, so the magnitude of the electric field is going to be twice as big. So we've got 2 times 4.495 times 10 to the 8 gives us 8.99 times 10 to the 8 newtons per coulomb. For the components, E3 points straight down, so the x component is 0. The y component is negative, and it's the whole thing. The magnitude of E4 is the same as the magnitude of E3 because they're the same charge at the same distance. E4 doesn't point up or down, so the y component is 0. The x component is to the left, so it's negative. Okay, for our vector sum, what we have to do is take the sum of all the x components. So we've got E1x plus E2x plus E3x plus E4x. So 0 minus 4.495 times 10 to the 8 plus 0 minus 8.99 times 10 to the 8 gives us minus 1.35 times 10 to the 9 newtons per coulomb. Sum of the electric fields in the y direction, we're going to add up all the y components. So minus 4.495 times 10 to the 8 plus 0 minus 8.99 times 10 to the 8 plus 0 gives us exactly the same number. We're not finished yet. These are the components. We have to write our electric field as a vector. So our net electric field is the x component with an I hat and the y component. And we have to make sure we include our units. So there's the total electric field at the center of that square. Part C now says if we put an electron at point P, find the net force on it. So we're placing a charge here at point P. We could repeat the entire problem as a vector sum using Coulomb's law, K Q1 Q2 over R squared, but that's the long way to do the problem. The easier way is to say that we know that I'm sorry if you heard that sneeze, that was my dog. He's lying really close to me. The easier way is to remember that force is charge times electric field. This is the charge in the field. This is the electron. This is the field that the electron is in, which we just found in part B. The charge of an electron is negative of the fundamental charge. So we're going to multiply that charge by this vector. And when we do that multiplication, what we get is positive 2.16 times 10 to the minus 10I plus 2.16 times 10 to the minus 10J with units of newtons. So there's the force on an electron at the center.